Or the second option is to choose ABC, non-credit. So if your score is lower than C minus, it's you can choose it to be non-credit. All right, so it's good they're offering the options to you. The university obviously recognize all the challenges this semester, and it's nice of them to give you the choices, especially if this has been a really tough semester for you. But there's a few things to consider, right? No credit doesn't mean you get a free pass, right? You still have to consider your GPA, still have to consider your graduation date. I do not know at this point if our class is still a prerequisite of hydraulic. I've heard different opinions. So you definitely want to consider the different options. If this is still a prerequisite to your hydraulic and you choose not to include the credit, that means you have to take it again, right? That means you have to take it again to improve your grades. And I can tell you that my next semester is already full, so there's no way for you to take this class again until at least 1 year later. So that obviously is it's going to delay your graduation date. So same thing goes to all the other classes. You have to think about how your grades is going to affect your GPA on top of your graduation date, right? You don't want to delay for another semester, so definitely think that through. It's an important decision for you. For me, as your professor, it does not change the way I graded your score. All right, I will grade you based on what we show you on the syllabus. I will grade you based on your quiz, your homework, your presentation. Okay, so that's not going to change on my end. I still grade you exactly the same way, and I will grade everybody. Okay, but it is going to be an important decision for you. All right, I see in the chat that somebody confirmed that they're taking hydraulic right now, so it's not a prerequisite. It does affect grad school. I believe the part that affects the grad school is GPA, right? And that's only affecting it if you're not getting good grades this semester. So I'll say the effect is limited, but it's really a person-to-person scenario. Okay, I wonder if you're taking hydraulic right now, Carla. How challenging has it been taking this and that at the same time? And how is this class related to hydraulics? They used to make this a prerequisite. Carla, do you mind share with us?
Only like one chapter really uses stats, but as long as you know how to find like standard deviation and a mean, like I think that's the only thing I've needed from this class.
Just mean and standard deviation?
Yeah, because everything else is just like specific formulas for that class. So.
I thought you just need that's probably why they removed this class as a prerequisite. Yeah. I also teach this class for industrial engineering, and they heavily relied on what we cover in this course as a continuation of other advanced classes. Okay, that's good to know. Okay, so I want to make that available, let you know that, so you have an important decision to make. All right, and Charlotte, since I already called out your name, can you be our last facilitator of this semester?
Sure.
Thank you. Okay, so for today, one last thing before we go to our class. Okay, you should be seeing the course schedule. Don't forget, we have our last homework, all right, and it's due after Thanksgiving. So definitely plan ahead of time. If you don't want to worry about the homework, you can choose to finish it ahead of time. Okay, the calculation with simple regression is not complicated. That's why it's simple, right? It's definitely not complicated. So if you want to make effort to that and complete it ahead of time, that's probably the preferred way, because after Thanksgiving, you probably just want to relax and start worry about your finals, right? So that's one thing. Don't forget, we have the final homework that's due after the Thanksgiving. And as for your final presentation, I want you to submit your presentation to Blackboard discussion board, just like how we did for the proposal and progress. But it is due before our presentation. Our presentation is on the 5th. I need you to turn it in on the 3rd, so I get a chance to review of your report before you present. Okay, so don't forget, don't miss those 2 due dates. Those are the last 2 due dates you need to remember about our class. Okay. Now let's go over our last chapter. Okay, regression. So share the content. Okay. So regression is not a new concept. We've covered this in chapter 6 in the very beginning of the semester when you plotted the 2 variables using a scatter plot. Okay, so some students like to do their project on, the aspects that improve that's related to their GPAs. They want to find out if study hours will affect their GPAs, or exercise time is going to affect their weight or body BMI. So those are the things that when you have 2 parameters in consideration and their correlation, that mathematical relationship is a regression model and will quantify the strength and the direction of that relationship with a correlation coefficient. All right. This presentation is similar to your textbook, but I like to use the presentation by these 2 professors. They're both from Cal State Fresno, from business administration. I liked how they use a lot of the graphics to explain the same idea, versus if you look at the presentation in your textbook, they include a lot of the equation to explain the idea. So I always prefer to use graphs to explain the equation. Okay, so what is a regression model? It is basically an empirical model. In a lot of the problems we encounter in the science world, in the engineering world, does not have a underlying equation to explain that. Not every phenomena has a Ohm's law to explain that, or has a Newton's function to explain the force. They just don't have a mathematical equation. And something is very specific to the engineering cases you have. So regression is an empirical model. In other words, we need to collect data and build a mathematical model to describe the relationship between the parameters that is specific to your case and your case only. So if you use your data and apply to it, let's say if you're analyzing baseball for this season, and use a regression model to apply to another team, it's not applicable, right? It is very data specific. All right, so we can analyze something that's specific for your data, and there's a lot we can do with our regression analysis. Okay, we can find out in this example, chemical process. We can find out how operating temperatures affect the yield of the product. And then based on that, we can adjust the temperature accordingly to maximize our yield. Or we can adjust the setting that gives us the most reliable yield, right? So there are different ways we can play with it once we identify the relationships between the input and the output. So regression analysis is used to build models, and you can even use that model to predict a new value. Okay, so if that's a value you have not studied before, regression analysis allows you to make some prediction. So regression is what we call a best fit mathematical equation. In other words, it's not going to fit all of your data points perfectly, but it's going to be our best predicting. And how do we quantify that it is the best predicting method? We need to introduce a concept called least square method in the next few slides to tell you how this is being done. Give me 1 sec real quick. All right, sorry about that. Have to pause for a second. Okay, so the method we use to generate this mathematical equation that describe the relationship of two variables are called least square. In other words, our goal is to minimize such equation. What is this equation? The y is your actual output. This y hat is a predicted value. Predicted value from your regression. So our goal is to minimize the differences between them. The actual quantity of the differences is how good your prediction, your model prediction is. So the smaller the prediction error is, the better your model is. So we're looking for such model that minimize your prediction error. So we'll refer this as prediction error. And I'll explain this square in a minute. Some of the prediction will be overestimate. Some of the prediction will be overestimate. We don't want those errors to be canceled out just because they're positive and negative. We want to capture each one of the error. That's why we're taking the square value. Very similar concept to the standard deviation we've talked about before. So let's go down and describe what is a regression model. So regression model is used to describe relationship of two parameters. Okay, if you're analyzing, scores, you can find out how a rush yard affects your touchdown or your score. You can analyze how does your batting rate will affect your final score or your winning odds, right? You can relate those two parameters based on a pair observation. One parameter and the other parameter. Sometimes this will be your input. Y will be your output. For example, number of hours put into study this course will be your input hours. Your output will be the grades, the grading you're receiving. Are they positively related? The more time you spend on study this material, the higher grades you'll get. We'll find out that relationship in a regression analysis. So ultimately, our goal is to find such line right here that describe my data. Okay, keep in mind this data, this line does not come over each data point. In other words, given a x value, here is my predicted y value. And this is my actual y value. So there does exist a prediction error. But our goal is to find such line that minimize such error. Okay? So given a x value, here is our predicted value. This is a predicted value. And how do we predict this value? We use this equation. Plugging my x0 into the equation to derive a mathematical output is our y hat. All right, so how can the two parameters affect each other? They could be positively related to one another. The older you are, the higher risk you might be for certain medical condition. The higher blood pressure you have, the higher the risk of certain medical condition, right? Or they could be negatively related. The more time you spend on exercising, the lower your body BMI will be. Those are the negative relationship. Pretty straightforward. Or there could be no relationship. A lot of times in a medical case, they will relate a medical condition to multiple aspects. So some aspects may not contribute to that medical condition at all. That's when we say there's no relationship between two factors. It is possible. All right, so now let's describe this regression. If you remember from your linear algebra, this is the basic form to describe a first order linear equation. Y equal to ax plus b. Okay, Over here, we'll use m for slope. By increasing x by 1 unit, how fast does y increase or decrease, right? Slope tells you the relationship. Positive slope, it means positive correlation. Negative slope is negative correlation. B here is intercept. When x equals to 0, what is the corresponding y value? Okay, so regression is basically a linear equation like that. Well, we'll elaborate more on that. So that's the base function of a regression model. We have a slope, we have an intercept. In a regression form, we simply change the notation from m and b to beta 0 and beta 1. Beta 0 is our intercept. Beta 1 is our slope. So the idea being exactly the same. The only thing we changed out is the notation. Okay. That being said, if you simply want to find out your grades and how is that related to study hours, you might find it positively related, but study hours may not be the only thing that affects it, right? So in the engineering world, a lot of times we will build a regression model like this. Why? Your output is related to your intercept plus beta 1 x1 relationship with the first parameter x1. There may be other parameters. There may be a second parameter x2, beta 2 x2. How is your study hour and number of units taken affect your grades, your GPAs, right? There could be other factors. And on top of that, there could be interaction between the two, right? Number of hours you can study really depends on how many units you're taking, x1, x2. Okay, so far it's been a linear relationship. Sometimes we're adding a second order model. Beta 1, 1, x1 squared, beta 2, 2, x2 squared. It can be all different ways to describe it. Okay, in this case, obviously, since we include the second order model, second order terms, it's not going to be linear anymore. But we've seen that a lot in the engineering world. A lot of the phenomena are just more complicated. In order to get the best fit, we'll have to go with a higher order and more complex model to fit our data, to get the empirical model of our data. So it is possible, but for our chapter, for chapter 11, we'll only have one parameter. Okay, it is a linear regression. Yeah.
Sorry to interrupt. The next after b of beta 1, beta 2 times x subscript 1 x. The next one is beta 1, 1 or just 1?
Beta 1, 1 to differentiate from the sub beta 1. Beta 1, 1 is the coefficient for x1 squared for the second order model.
Oh,
so this one will be beta 2, 2. Let me write that again. So that's why in the engineering world, we use beta 0 and beta 1. That allows us to have the flexibility to add in more model terms into a simple linear regression. Okay? This is referred to as a simple linear regression because we only have one parameter, and we assume that's a linear relationship. Okay? Now, in terms of the way we write our model, as we described before, y is our dependent variable. Okay, so your GPA, the result of your GPA depends on how much time you put into study of the subject. So y is a dependent variable. It depends on our x. X is an independent variable. In other words, if you have to include multiple x's, so your study hours, your GPA may be related to how many units you're taking, how many times you spend on study, all of the subject. Those two parameters, those two x's should be independent from one another. Okay, you're analyzing your GPA from different independent aspects. They should not be correlated to one another. Okay, so x is our independent variable, while y is dependent. It is depending on our input variable x. So beta 0 is what we use for intercept. Beta 1 is regression. Okay, something that's important that we did not cover in your linear algebra is this form, random error. This is to describe the differences between the predicted value versus actual value. If we add in this random error, which could be positive or negative, it will bring in the predicted value to be exactly the same as actual value. So your actual value of y is the predicted y, which is this equation, plus their estimation error. Okay, so if I put estimation error on this side, it is the actual output, and the difference is from the prediction value. Okay, so this one, random error, is very important. There's a lot of application based on the residual. We'll only discuss the basic application in here, which is our least square function. We're looking for the regression line that minimizes such error, that minimize our prediction error, and that's our best fit of the data, and that's our regression equation. All right. So here is how we calculate the estimation error. First of all, you have your actual data. This is the data you collect from your experiments. And here is a predicted value. This predicted value is based on a selected regression model. Could be anyone. So the differences between them is our estimation error. Sometimes we use epsilon, sometimes we use error, sometimes we refer to as residuals. Sometimes we refer to that as error or prediction error. Same thing, okay? Don't let it throw you off. It's just notation and terminology. Error or epsilon. Same thing. All of this notation are used to describe the differences between your actual data from the predicted data calculated from your regression model. So here is another estimation error. The difference is from the actual to the predicted. Here is another one. All right. Those are our residuals, right? The difference between actual and predicted. Keep in mind, in this case, actual is lower than predict. So this value will be negative. This one, actual, is higher than predict. This error is going to be positive. If we add up all this error, this positive and this negative will be canceled out. So for us to capture each one of them, we are going to add up the squares of each estimation error, which leads us to the next slide. This is how we capture it, and we refer that as a square error. The square error is captured by calculating the differences between actual value and predicted value. And this predicted value is based on plugging x1, our independent variable, into our regression equation. So that differences is our error. And again, as I mentioned before, to avoid cancelled out of the positive and negative errors, we take the square to capture the error. Now, this is the only error based on one x value, x1. Ultimately, we want to add up all of the estimation error. If you have 10 x points, we want to capture that 10 estimation error. So this is what we refer to as sum of error, SSE. This is the sum square of all of the error value. So we're capturing capturing all of the prediction error. After we capture all the prediction error, then we can minimize. We can find such line with a given beta 0 and beta 1 value that minimize this sum square error. In other words, it minimizes our prediction error. So in turn, it should give us the most accurate regression model. So this is our least square. Okay. In our class, we don't discuss in detail how do we derive the sum square. Okay. How do we get to these terms and how do we find the beta 0 and beta 1? We'll just give you the equation. Okay, so there exists so many different lines here with different intercept, with different slope. How do we know which line best describe our data? We'll find such line with the intercept and the slope that allows us to minimize the prediction error, the sum square error. And that is our least square method. All right? So this is part we skip, but from your calculus, to find the best value, we take the first derivative of our sum square error and set that to 0. That allows us to find such beta 0 and beta 1 value that minimize that sum square error. That's how we typically find the best value to find a solution of our first derivative. So here is how we derive that value. Okay, so we won't go to the detail of how do we derive that equation, but we'll just give you the equation here. All right, we'll give you the equation here. You can either use this equation to derive those beta 0 or beta 1, or after we go through all the slides, I will show you how to do this in Excel and ETAB. Okay, there's gonna be 10 questions in your homework. You can choose to use either one. Okay, so keep this question. Let's go to an example. A very simple example. If you took AP statistics, you probably went through this type of example already. So we've collected data of 8 employees, and we wanted to find out if their service years in the company will affect their ownership of the company stock. So here are our 8 employees. X is their number of service years. Y is their stock share. So question A, determine the least squares regression line and interpret the slope. So I will reword this question to use a least square regression to identify the relationship between service years to their stock shares. Okay, we're going to use a mathematical equation to describe the relationship of those two parameters. And then another very useful part of the regression analysis is that we can use the regression to make prediction. For an employee who has been with the company for 10 years, what is the predicted number of shares of the stock owned? So we can use our regression after we identify that beta 0 and beta 1, use that for prediction. Okay, we know this is a line, this is a regression line we've identified that minimize our prediction error. So it is our best bet to use this equation to make a prediction. All right, so here is our x and y, and the product of xy and x squared is for you to utilize it in the equation to derive your beta 0 and beta 1. Okay, so utilize the equation given. Here is our beta 1 and 0. And then we can put together our regression. Okay, and they put this best fit under quotation. It's because it's not going to estimate every single data point accurately, 100% accurate, but it is the best one we can find based on least square method. It is the regression that's going to minimize all of the estimation error. So the estimation error is minimized, but it's not 0. That's what they meant by best fit. Okay, so based on this regression, we know they are positively correlated. The more number of service years you have in the same company, the more stock you will own within the company. All right. Next, here is a Minitab output. It's pretty straightforward. The dots, without looking at the regression line, is positively correlated, and that's our regression line generated using least square method. As you can see, there is estimation here, estimation error here, estimation error, estimation error. Okay, so there's estimation error in here, but they are minimized. Okay. Next, let's use this regression model to estimate it. If a person has been working in this company for 10 years, his estimated share of stocks will be 432 shares. Right? The calculation, the mathematical calculation is pretty simple. You guys shouldn't have any problem deriving this. What I want to point out here is that this prediction, we like to look at our raw data. If you look at our raw data, the number of service years, our X value, are ranging from 6 years to the high end will be 15. Right? That's our data range. So when it comes to prediction, our model will be fairly accurate if the data is within this range, because we have our model is built based on this data. Okay, so back to here, let me erase this. As long as your predicted value is within this range, from 6 years all the way to 15 years, any data in this data points within this range will be fairly accurate. But beyond this point, the stock share is not going to increase linearly. Maybe it's going to slow down at some point. Then linear model may not apply. Or in the beginning, it increased a whole lot faster than just a linear, right? So out of our data range, the predictability will lose its accuracy. So regression, that's the limitation of regression, is best estimated for the data that's within our data range. Once outside the data range, we lose that accuracy of predictability. We simply don't know what it looks like. Okay? Now, to describe if they're positively correlated, negatively correlated, or how strong two parameters are related to each other, we quantify that by using coefficient of correlation, lowercase r. It is a value that we standardize all of the estimation to plus minus 1. So that's a standardized value, but it's very easy to interpret because the positive and negatives will tell us the direction they're related. The value will tell us how strong they're related to each other. If the correlation coefficient is 0, that means the two parameters are not related to one another at all. If they're close to plus minus 1, let me go to this one. Okay, if your lowercase r is close to positive 1, negative 1, that means they are strongly correlated. Could be positive, could be negative, depends on the sign. If it is below if it's below 0.5, whether it's positive or negative, they are weakly correlated. If it's 0, that means the two parameters are not related to one another. Okay, pretty straightforward, easy to understand. That's why they standardize it. Which comes to this chart. Even we don't know all the data over here, we can have a relative R based on what the graph, based on what the scatter plot looks like. In this case, negatively correlated, right? And all the data points follows a straight line. So we know the correlation coefficient will be strong negative correlated. Same thing on figure 5. All follows a straight line. The higher the x is, the higher the y is. We know they are strong, positive, correlated. Next, let's look at figure 2. Still, you can still see the trend is positive, even if it doesn't follow the straight line, but the trend is pretty obvious. So we know this is R is probably greater than positive 0.5. That means they are strong, positively correlated. Same thing over here. Negative correlated, we can see a pretty obvious trend. So this will probably be less than negative 0.5. Okay. With respect to figure 3 and figure 4, given a x value, I'll randomly pick the x value. There are so many y value correspond to one given x value. In other words, the x value does not help us to predict the value of y, right? There's so many corresponding y values over here. That means they are not related. Okay, they have 0 correlation coefficient. Okay. Compared to hypothesis testing, this is pretty straightforward and mathematically straightforward. Okay. Skip this one. We covered this already. So here is the equation. You're gonna need to carry out the mathematical equation for correlation coefficient. Okay. You can either use this given equation, or I will show you how to do this in Minitab and Excel. So let's use this equation to the previous example we've used. Okay. Here are x is our number service years. Y is their stop share. We already derived their intercept and slope. Here is our correlation coefficient using the equation. Okay, positive 0.84, it is positive. It is greater than 0.5. We know the number of stock share is highly correlated to the number of service years. Okay, so I believe most of your project, this is applicable to most of your homework. I like you to see, you perform a regression analysis on the 2 parameters you're interested in your data. How is your scoring affected by different aspects of the statistics collected? Now, how do we utilize things we already learned and applying it onto our regression analysis? We can perform hypothesis testing on regression analysis. Okay, so what are we testing for? Sometimes we can generate regression model, but doesn't mean their relationship are linearly related. Okay, so we can perform a hypothesis testing to test it. This is what we're testing. We're testing on the correlation coefficient. The null hypothesis assumes R is 0. That means there's no linear relationship exists. They're not related to one another. Or R is not equal to 0. There's some sort of a linear relationship correlating these 2 parameters, either positive or negative. We don't know. We'll have to generate regression to find out what it is. And here is our test statistic. Okay, you need to calculate your correlation coefficient to derive your t-value. Compare your t-value to your critical value and determine if you're going to fail to reject the H0 and conclude there's no linear relationship, or reject the H0 and conclude, yes, there exists a linear relationship between the 2 parameters. Okay, we all know how much you feel about hypothesis testing. So I just want to point out the fact that it can be tested, but you're not going to be asked to perform hypothesis testing here. Okay, just want to lay it out loud there. So just knowing that it can be tested, because a lot of times we are generating regression, but we couldn't make it a decision that if their linear relationship exists or not. So that would take one extra step to confirm that by performing a hypothesis testing on the linearity. Okay, the good news is that's all I wanted to cover today. Okay, but you will have 10 questions to practice everything we've covered today. Okay, so go over that 10 question on your whiteboard. There's no quiz on chapter 11. Today is our last quiz today. Okay, so after that we're done with all the testing, but if this is applicable to your project, I would like to see that. If you don't perform that, but I see that it's applicable, I will either take points off and ask you to perform that. Okay?
So these slides are not up, correct? Because I looked at I downloaded the Wileys they're not even close to the
yeah, the slides are available. The slides given to you are based on your textbook.
Okay, yeah,
so the idea being exactly the same. Yeah, if you look at the equation, they're exactly the same. What I like about the slides is that they offer more graphs. It's easier to interpret the idea to use the graphs, while the equations are the same.
Yes, a little bit. Okay, thank you, Professor. Yeah, they're a lot different than what you're starting on.
Yeah, it's just don't let the equation throw you off. They're identical. If you like, you can sketch it on your own notebook, or you can sketch it next to the slide. What I wanted to cover now, yeah. Other questions?
Do you mind posting these slides?
This one?
Yeah.
Yes.
Yeah, I can post it.
Awesome.
But I'm going to ask you not to use it otherwise.
Okay.
Okay, you can use it for your homework. You can use it for your project, but please do not use it beyond this class. I have the same concern as my recording, so I just want to put it out there. I do want to help you as much as I can. Okay.
Thank you. I appreciate it. All of us appreciate it.
All right. So the last thing I wanted to do is to show you how to perform this on Excel and in Minitab. By doing so, I think will be really helpful to show you one example that's very similar to your project and explain to you what I expect to see from all of your project. Okay, Carla, are you seeing a CPP exit survey?
Yeah. Yes.
Okay, great. So this is a small project I did with Career Center, CPP Career Center. There's an exit survey. They send out to all the graduates. Before they can collect their diploma, they have to fill out a survey. This survey mainly will help Career Center to help the future students. What they found helpful to all the graduates to help them to land a job or find a internship or help them with their interviews. So they collect a lot of different aspects from the graduates. So the only thing I use here is the relevant data, which are students in the College of Engineering. Okay, so that's what the project is mainly about. You're gonna have the same slides, talks about your project, where do you collect your data, and what are you trying to find out. So first, I wanted to know, how is the starting salary different across different engineering degrees? It makes more sense to compare different engineering degrees, so we're comparing apple to apple. Even our application is still very different, but at least we are the same type of degree. So over here, I choose to use a descriptive statistics. I choose to use a box plot because it's a very useful plot for you to compare multiple data sets together. You can certainly generate, how many do I have? 8 different box plots separately, but it makes more sense to put them side by side so you compare one another. Over here, it's showing pretty clearly that aerospace has a lot of outliers. For some reason, they maybe it's their graduate degree or whatever it is. They have a lot of people with their salary on the high end. It's not a bad thing, in this case, it's not a bad thing. But for the rest of the data, it's really consistent for aerospace engineering. And most of the salaries are fairly consistent, with the highest salary in chemical and material engineering, and the other one is probably engineering technology. You can visualize this data and direct those observations right away. That's the power of graphical statistics. So pick and choose the graph you want to use carefully, so that it gets the idea across the board easily. Everybody can look at this chart and learn a few things from here, right? And the one with the highest variation is probably mechanical, with the whiskers going all the way up to almost 14,000, and a lot of variability there. Another one is chemical and material engineering. Even their averages are high, there's a lot of variability in here. How do I know there's a lot of variability? Remember in the box whisker plot, the length of the box is your IQR. What is IQR? It is the differences between your third quartile to first quartile. So the length of the box tells you how much variation you have. So IQR is a way to evaluate your variation. Okay, so this ties in a lot of aspects we've covered, and it also shows you a lot of important information just by using one plot. So I wanted to see you utilizing a variety of charts wisely and pick the one that shows the most important information. Okay? Next, I want to show you a one sample hypothesis testing, and this is a very important question. In the average starting salary of students with engineering degree, is their starting salary higher than 48,000? Okay, so very simple. I get a 48,000 from a national average of engineering entry-level engineers, and I wanted to know our data. In other words, students with an engineering degree from Cal Poly Pomona, do they meet that average, national average, or are they higher than that? Okay, this is how I carry out the analysis. I want to show you this one in Minitab and the next one in Excel. Same analysis. You can choose either way. I want to emphasize on either way. I don't need you to perform both. As long as you pick one that you're used to, then the conclusion will be exactly the same. Pick one that you're used to. However, make sure you put together your hypothesis statement, all right? And highlight the important part. For example, p-value is less than 0.05. We reject the null hypothesis and conclude. I wanted to see your conclusion stated that. What does this conclusion mean by rejecting the null hypothesis? What does that mean to your project? In my case, rejecting that means the starting average salary of an engineering major student is greater than 48,000. And this is an important conclusion, very useful conclusion, because once you receive the degree, you're going to go out and go over interviews. A big question is always, how much should I ask for? I don't want to ask for too much, people will turn me down. I don't want to ask for too little, then it's not going to help me financially at all. So this is backed up by data. This is a reasonable salary to ask for. This is supported by our hypothesis testing. So this shows you how useful hypothesis testing is, despite how complicated the concept is. Now, if you choose to use Excel, that's fine with me. I would like you to highlight if you use a one-tail or two-tail test. If you look up on the right-hand side, mine is a one-sided hypothesis testing with population variance unknown, right? So I test my data against 48,000. Okay, and it's a t-test because I don't know the population variance. So I highlighted this one. I draw my conclusion. Conclusion is exactly the same. Carry on. I wanted to do a two-sample hypothesis testing by comparing the starting salary between the business major student from the engineering major students. Okay. Minitab carries out the two-sample hypothesis testing. Remember, Minitab doesn't give you critical value. So the only way for you to draw a conclusion is to look at the p-value. p-value less than 0.05, less than your alpha, we reject the null hypothesis. All right, so put your hypothesis statement on there so I understand what is the hypothesis testing about. You have to put it on there, even you don't have to include it in your Minitab. Okay. I wanted to know if the two populations have the same starting salary, or more importantly, since we're all engineering major, I wanted to know if our starting salary is higher. Okay. So the result is to reject the null hypothesis and conclude engineering major did have higher salary than a business major. You can do the same thing with Excel. And here's the rule of thumb. I can't say it for all of your project, but here are the two rules of thumb for your project. First one, for most of your project, we don't know what is the population variance. So you definitely want to choose the case that population variance or variances are unknown. Second of all, do not choose your alternative hypothesis as not equal to. In most of the engineering cases, we wanted to know if it's greater than or less than. Not equal to doesn't really give us as much information. Greater than or less than will give you more information. I wanted to know in this case, there's no point for me to know engineering starting salary is not the same as business. I definitely wanted to know who's higher, right? So think about how you want to put together your hypothesis statement. It is more important than you think, all right? Set it up wisely, then you can carry out the rest of the analysis and gain important information from your data, right? Simple regression. This is what I want to demonstrate today. I want to use a simple regression to show how is GPA related to your salary. Is a higher GPA means you have a higher salary? I want to show that to you. Okay, so let's start with Minitab. Let me share my Minitab. Okay, should be seeing my Minitab right now. I have my GPA in one column, my annual salary in another column. Okay, let's go to stat. If you recall, most of the analysis we have done so far is under basic statistics. This is the only exception. Okay, the last chapter will use regression. Okay, I will only use the first one, fitted line plot. I want to generate a regression plot, and also the analysis will show you the hypothesis testing. Okay. So my Y is my annual salary and my X is GPA. Since we're generating a simple regression, I'm going to select a linear regression. All right, so this is our regression. Okay, that's our intercept. That's our slope. And R squared, if you recall from our coefficient correlation, is a lowercase r. Okay, I can't write it here. Lowercase r is between -1 to +1, but statistically, we always take the square of that. Okay, that's another statistic we didn't discuss a lot today, but we use it a lot in statistics in engineering, and that is the coefficient of determination. It is the square of your lowercase r. So if lowercase r is between -1 to +1, r squared is between 0 to +1 because it is a square. The higher that r square is, the higher the regression model explains your data. Okay, the higher related the two parameters is. Okay. Here is a hypothesis testing. We didn't really cover analysis of variance. The only thing you can tell is the p-value. So basically, analysis of variance is also a hypothesis testing, but instead of using z statistic or t statistics, they use f statistic. And the only conclusion we can learn from here is the p-value. P-value tells you how significant this regression is. Does this regression model helps you to explain the relationship between the two parameters. And it is less than 0.05. All right? Most importantly, the regression plot. Since I have a lot of value, I think I have more than 300 data points. So that's what my data looks like. They are slightly positive. My R square is 1.4, which means they are weakly correlated, weakly positive correlated. So it's fair to say that GPA affects your annual salary very limitedly. There are other factors that's going to contribute, that's going to add up and contribute to your starting salary. Has something to do with your related experience, has something to do with maybe your extra curriculum, has something to do with how did you perform, how well did you perform in during an interview, things like that. And every company has a different policy, has different benefits. All of these are affected. So it doesn't mean we can rule out the importance of a GPA. It's not exclusive. But if we want to increase the accuracy, we need to add in more aspects to increase our R square. Okay, that's the most important conclusion we derive from here. GPA is not the only thing explaining your starting salary. There's more aspects, more X factors, X variables that will add up to determine your starting salary. Right? Last, I want to show you the same analysis in Excel, and you decide which one you're more used to. Okay, here are the two parameters. You should be seeing my Excel. Here's my GPA. Here is my starting salary. By default in Excel, the first column is going to be your x-axis in the scatter plot. The second column is going to be your y. If your order is reversed, you can choose to sequence them differently, or you can generate the scatter plot, and in the function you can choose to switch the x and y's. So I'm going to select all of my data, go to insert, and I'm going to scatter plot. There are many options over here. I don't want any line. I don't want any lines to connect our data. It looks very messy. It does not. It also it doesn't allow you to perform regression analysis. So select the basic one, just dots, just the scatter dots. All right. To make the data more clear, I'm going to change the axis. The GPA starts at 2, so I'm going to change the lower bound to 2. And the high end, it doesn't go any higher than 4.0, so I'm going to end it at 4. Now the data looks more centralized. Even if X doesn't start at 0, that's okay. Now I'm going to zoom in a little more so you have a better view of this. To generate a regression, pretty straightforward. Go to the dot, select one of the dots. As long as you right-click on one of the data points, you will have the option to add a trend line. Again, go to any of your data points over here, but it has to be right-click on one of the data points. Select Add Trend Line. Okay, again, we're generating a simple regression. Okay, select a linear equation and scroll to the bottom. Choose to include the equation, regression equation on the chart. Choose to include the R square on the chart. Again, R square is the square of coefficient of correlation. Okay, again, R square is really low. They're weakly correlated, and you'll see a line here. Okay, you can if it's not very well shown, I think you have the option to highlight it more. You can choose colors of line, you can increase the width of it to make it more obvious, and you can also choose a smaller one. But anyways, you have different ways to add your regression line, but that's how you perform analysis. Okay? Any me see if there's anything else I need to cover from Excel. Let me see if there's a question. Okay, all right. So that's all I wanted to cover today. Okay. Is there any question before we start our quiz? Okay. If not, let's take a 5-minute break and we'll start a quiz. Okay. I'm going to protect it here.
Thank you very much, Professor. Are we gonna meet next Saturday?